Hi girls, we're just going to pick up where we left off in class talking about the law of conservation of momentum and solve some problems using it. So remember, what the law of conservation of momentum tells us is that if two objects collide, if we find the sum of the momentum of each of the objects before the collision, that's going to equal to the sum of the momentum of the objects after the collision. It does not mean that the individual objects cannot change their momentum before the collision and after the collision. It just means the sum has to be the same. So however much you have total on the left before the collision is equal to how much you have total on the right after the collision. So let's look at an example. Here we have a truck driving along the road, not paying attention, rear ends a car that's sitting at the stoplight. After the collision, the car starts to move ahead in the direction that the truck was initially traveling with some speed, and we want to know what the speed of the truck is after the collision. Now, one way you can help yourself solve these problems easily is to make sure that you're pretty well organized. And one of your first ways to do that is to know which object is which. So I'm going to start to look at my truck, and I'm going to call it object number 1, and I'm going to call my car object number 2. Now I also want to make sure that I have some direction information. So I'm going to say initially, here is my truck moving in the positive direction, and of course my car is not moving at all. And then after the collision, I know that my car is going to move away in the direction that the truck was initially moving. I'm going to still call that the positive direction, but I'm not quite sure about the direction of the truck after the collision. I'm going to let the sign information that comes out of my solution tell me what direction it's moving in. Okay, so let's look at writing down what we would use for our conservation of momentum. For momentum, we take mass times velocity. So for object 1, our truck, it's its mass times its initial velocity plus the mass of my car. That's object 2 times its initial velocity. That's the sum of the momentum beforehand. We know that's going to be equal to the mass of the truck after the collision multiplied by its velocity plus the mass of our car multiplied by its velocity. So that's our total momentum after the collision. So what we want to look at is maybe trying to simplify this as much as possible. From our problem, we know that our car is not moving before the collision, so we know it has no momentum. So this guy is 0. He goes away. So that leaves us with just all the momentum in the beginning, before the collision, is just the momentum of the truck. Right? So in order to now find the velocity of the speed of the truck afterwards, this is the guy we're looking for. So let's do a little bit of rearranging. I'm going to try and isolate that final velocity of the truck. I'm going to bring over and this is still the guy I'm looking for. So I'm going to divide each side by the mass of my truck. Okay, so the final speed of my truck is the mass of my truck, which was 2,500 kilograms, times its velocity, which was the 15.6 meters per second. All right, I'm going to leave out all the units here, times now the momentum of my car, and its final velocity divided by the mass of my truck again. Okay, and when I look at that and do that math, I get an answer that the final velocity of my truck after the collision, it's a positive number, and it's 13.2 meters per second. Okay, so what that tells me, first of all, is that the truck is still moving in the same direction it was initially moving in. That's what the positive sign tells me. And that it gave, if you want to think about it, some of its momentum to the car. So the fact that the car got momentum out of the collision means that the truck had to lose momentum out of the collision, which if you look at it, and if you had actually gone back and figured out numerically how much momentum the truck had had beforehand, which is this number here, you can see that it would have had more momentum there because it's going faster. Okay, let's look at another example. In this case, I'm going to try and do the problems a little bit different each time so that you can give yourself an idea of different ways to approach doing these problems. So here we have two football players. We have one lineman moving at 2 meters per second, and he tackles another football player moving at another speed head on. So this means a collision where they're moving in opposite directions to begin with. After the collision, both of them move together. All right, so they stick together. So you remember in class we talked about one of those types of collisions is where objects are initially separated, but when they collide, they stick together. So now, in order to have that closed system, we can't lose any mass. So whereas we have two objects beforehand, we now just have one object afterwards, but the mass of that object is just the sum of the masses of the individual objects. So again, it wants to know how fast they're moving after the fact. So again, know which one is which. So I'm going to call my 120 kilogram guy number 1, and I'm going to call my 80 kilogram guy number 2. All right, I'm going to say that number 1 is moving in the positive direction. And I'm going to say number 2, simply because I know that's a head-on collision. I know that they're moving in opposite directions. I'm going to say that number 2 is moving in the negative direction. Just making sure that I know what I need to do. Okay, so here's another way that you can approach it if you want. You can look at it from a table perspective if you want. So you can look at the momentum beforehand and then the momentum afterwards. You can just sort of sum them up. So if I look at initial momentum, all right, I'm going to have for object 1 his mass plus his velocity, and I'm going to have for object 2 his mass and his velocity. So from my problem, I know that this one was 120 kilograms. And remember, he was moving at 2 meters per second. So his initial momentum is 240. All right. And I know from this guy, his mass is 80 kilograms. And his velocity, now he's going in the opposite direction, is a negative 5.5. So that tells me his momentum is a negative 440. All right, if I want to sum them up, I just add those two numbers together. All right, so 240 plus a negative 440 tells me that my initial momentum for my conservation of momentum is equal to negative 200. And here's where you can start to add in your units if you want to make sure that you have your units there. All right, so that's my initial momentum, the sum of my two objects. Now if I want to look at my final, all right, this is where you have to start to look at what works for you. So for my final momentum, my objects are actually moving as one thing. So my mass of my object is actually the sum of the two masses. And they both travel away together at the same speed. When things stick together, their final velocity, it's the same for each because it's really moving now as one object. So that's going to be equal to the sum of the two masses, which is 120, plus 80. And 120 plus 80 is 200. And this is the guy that we're looking for. So now we can just set that equal. We can go negative 200 kilogram meters per second, which is our initial momentum, is equal to our final momentum, and a little bit of division would give us that our final velocity of our football pair is -1 meters per second. So what that tells us is they each had a certain momentum, they collided, they stuck together, they move away both more slowly than either of them originally moved, and that sort of makes sense because now the object is more massive, and that they move in the direction of the 80 kilogram fullback. Remember, he was the guy that was moving in the negative direction, and since our answer comes out to be negative, that must mean that's the direction that the pair of football players are moving together as a unit after the collision. Okay, so you can use algebra, you can use a table, you can use whatever works best for you to keep your information organized. Okay, and now we have one more. We have a 15-gram marble. It's moving to the right. It makes an elastic collision, and that's something we're going to learn about more when we talk about an energy, with another marble moving to the left. Right, so after the collision, it tells us something about how the smaller marble moves, and it wants us to know what's the velocity of the other shooter marble after the collision. So same kind of thing. Always start out with some definition of which object is which. So number one for me is going to be my 15-gram marble. Number two is going to be my 30-gram shooter marble. I don't know how many of you have ever played marbles, but the shooter is the bigger marble. All right, so again, we want to look at some direction information. So our 15-gram marble is moving to the right, so let's make that the positive direction. And we know then that our 30-gram shooter marble is moving to the left, so he's moving in the negative direction. So we know after the fact, if we say this is the before, that the smaller marble, the 15-gram marble, now changes direction as part of the collision. So after it, it tells us that the smaller marble moves to the left. So you want to make sure that you realize that the velocity of the marble after the collision is in the negative direction. All right, so again, let's look at our solution. I'm going to use the algebra way because it's just the way I use it. But this time what I'm going to do is to make life easier for you, I'm going to substitute all the numbers first before I do any of the algebra rearrangement. And again, that's just to show you that there's a couple of different ways that you can do these. You just have to do what works best for you. Organization is the key though. All right, so our law of conservation of momentum tells us all about the relationship between the initial momentum and the final momentum. All right, we don't have any zeros in here, so we can't clean anything out, but we do know what we're looking for. We're looking for the momentum, or excuse me, the velocity of my second marble as it goes away. I know all the other pieces of information. So this is where I'm going to go, and I'm just going to substitute my numbers in there to make it easier for you. If you do it this way, just watch the signs. First thing to recognize, though, is that you really have to be careful with your masses in here. Remember, kilogram meters per second is your standard unit for momentum, so your masses have to be in kilograms. Both of your masses in your problems were given to you in grams, so they have to be converted. So for our first one, our mass of our marble, remember it was originally 15 grams, so that means it's 0.015 kilograms. Its velocity is 0.225 meters per second. Okay. Our shooter marble, again, it was in grams. We want to make sure it's in kilograms. It was 30 grams, so that's 0.03 kilograms times its velocity, and it was moving to the left, so you got to make sure you put that negative sign in there. Okay, that's our one side of our equation, and we know that's going to equal to our other side of our equation. So again, our first mass times its velocity after the collision, which now is in the negative direction, plus the mass of our shooter marble times its unknown final velocity. Okay, so now when you go through all your math in here, you should be able to add these together, making sure that you realize that one of them is negative. Then when you bring this guy over, you want to make sure you realize that you're adding it to each side because it was negative on the side it was on. And we come out with our final velocity for our shooter marble turns out to be a positive 0.09 meters per second, which means that essentially our two marbles came towards each other, they collided, and then they bounced back away from each other. Okay, you might notice some of the change of what happens as far as their changes in velocities. It kind of makes sense if you look at some of the information. Marble 1, the smaller one, was initially moving with this speed. All right, think about the size of the velocity. When it moved away, it was going faster, even though it was going in the opposite direction. That must mean, because of our sum of our momentum, that our shooter marble that was initially moving at this speed, he sort of gave some momentum or some speed to our smaller marble. So as a result, in order to do that, his speed has to become less so that it has less momentum afterwards. Okay? Whichever approach you want to use. You want to use the algebraic approach, you want to use a table approach, you want to do this one and calculate each of the individual momentums before you move things around. That's up to you. What you just have to make sure is that you really stay organized. Make sure you know which object is which. Make sure you know whether the velocity information given is from the initial, before the collision, or the final, after the collision. And make sure you know what direction each of the velocities is in. And last but not least, the most important thing, when you're doing your algebra or your math, please be very careful with the signs. When you're moving things around, addition and subtraction makes a big difference which way you do it. Okay? With that, you should be able to do some of the problems that you were assigned from your textbook. We will work on the rest of them, whichever ones you can't do, in class the next time we meet. Thanks. Bye.